Hello everyone, my name is Sushmeet Kaur Saluja, currently pursuing MCA from IIPS DAVV. In this video, I am going to explain the topic of dimensionality reduction in machine learning, and we will also compare feature selection and feature extraction in detail. By the end of this video, you will have a complete understanding of why dimensionality reduction is important, how it works, and when to use which technique. So let's begin. First, let's start with the introduction to dimensionality reduction. In machine learning, we often work with datasets that have many features or variables. These features may contain useful information, but sometimes having too many features leads to problems. Models become slower, training time increases, and accuracy decreases due to overfitting. Dimensionality reduction is a technique that reduces the number of input features while still retaining the most important information. In simple words, it is a process of transforming high-dimensional data into a smaller number of dimensions without losing meaningful patterns. This helps improve model efficiency and performance. So, dimensionality reduction is extremely important for building accurate, fast, and reliable machine learning models. To understand how dimensionality reduction works, imagine a dataset in three-dimensional space with axes x, y, and z. Suppose most of the data patterns or variants lie only on x and y axis. This means z-axis contributes very little to understand the structure of the data. In such a case, the z-dimension can be removed and the data can be represented accurately in just two dimensions, x and y. This removal of unnecessary or less informative dimensions in the essence of dimensionality reduction. We reduce the dimensions so that the final dataset becomes easier to process while keeping the essential information intact. To make this concept easier, let's look at an example. Example dataset. The dataset contains information about students and includes three features: height, weight, and kilogram, weight in kilogram, and BMI. We have three students: student A with height 170 cm, weight 65 kg, and BMI 22.5. Student B with height 160 cm, weight 70 kg, and BMI 27.3. Student C with height 180 cm, weight 75 kg, and BMI 23.1. Now let's understand what this table actually shows. There are three features: height, weight, and BMI. But BMI is not an important value. BMI is calculated from height and weight using a formula. This means it doesn't provide new information. Because BMI depends on height and weight, it becomes a redundant feature. So even though the dataset shows three columns, the core information exists only in two dimensions, height and weight. By removing BMI, we reduce the dimensionality from three features to two without losing any meaningful information. This example shows how dimensionality reduction simplifies data. Now, why do we reduce dimensions? The answer is simple. Too many features create several problems. First, models take more time to train. Second, large feature sets require more storage and higher computational power. Third, too many features can cause overfitting, where the model learns unnecessary patterns and perform poorly on new data. By reducing the number of dimensions, we make the model simpler and more efficient. We also improve generalization, meaning the model performs better on unseen data. Dimensionality reduction helps in faster training, less memory usage, reduced overfitting, easier visualization, and overall improved model performance. Now let's move on the first major approach to dimensionality reduction, which is feature selection. Feature selection means choosing only the most important features from the original data set. We do not create new features here. We simply select the best one. Feature selection enhances accuracy, reduces overfitting, and makes the model easier to interpret. There are three main types of feature selection methods. Filter methods. These methods use statistical technique like correlation, chi-square tests, information gain, or variance thresholding to select relevant features. They are fast and independent of machine learning models. Second is wrapper methods. Wrapper methods test different combinations of features by training a model repeatedly. Examples include forward selection, backward elimination, and recursive feature elimination. These methods are more accurate but also more time consuming. Now third is embedded methods. Embedded methods perform feature selection during model training. Example includes lasso regression, ridge regression, and decision tree based methods. They combine the advantages of both filter and wrapper methods. Feature selection is especially useful when we want a simple interpretable model. The second major approach is feature extraction. Unlike feature selection, feature extraction does not choose existing features. Instead, it transforms the original features into a new set of meaningful features. The goal is to compress information from multiple features into fewer, more informative components. Feature extraction is extremely powerful when the dataset is complex or has nonlinear patterns. Some of the most popular feature extractions techniques include PCA, Principal Component Analysis. PCA converts original features into new variables called principal components. These components capture maximum variance with minimum dimensions. LDA, Linear Discriminant Analysis. LDA finds new axes that maximize the separation between multiple classes. Third is kernel PCA. Kernel PCA handles nonlinear relationships by projecting data into higher dimensional spaces. Autoencoders. Autoencoders are neural networks that learn compressed representations of the data. They are powerful for image, text, and high dimensional data. Feature extraction is ideal when raw data is complex, noisy, or not easily distinguishable. Finally, let's compare feature selection and feature extraction. Now, feature selection chooses the best subset of the original features, while feature extraction transforms the original features into a new feature space. Feature selection keeps the original features intact so interpretation becomes easier. Feature extraction may reduce interpretability but often improves performance and captures complex patterns. Feature selection methods include filter, wrapper, and embedded techniques. Feature extraction methods included PCA, LDA, kernel PCA, and autoencoders. Both techniques reduce dimensionality, but they work in different ways depending on the nature of the data and the problem being solved. So thank you so much for watching this detailed explanation of dimensionality reduction feature selection, and feature extraction. If this video helped you to understand the concept clearly, please make sure to like and share. If you need scripts, notes, or explanation for more assignments questions, feel free to comment below. See you in the next video. Thank you guys.